Hi everyone again, I'm Han, and I will be presenting this paper on behalf of Xinyi, who is unfortunately cannot be here today. So today I'm pleased to present SwiftEP on behalf of them, the work on accelerating a mixture of efforts inference with buffer fusion and TMA offloading. So let me start with the model context. Mixture of experts, or MoE, replaces a dense feed-forward network with many experts while activating only a small subset of each token. This improves scaling efficiency. During inference, the prefill phase processes the whole prompt in parallel, while the decode phase generates tokens one by one. The prefill phase is both computation intensive and communication intensive. This work focuses more on the prefill state. When these experts are distributed across GPUs, we use expert parallelism. Then every MoE layer introduces two communication phases. Dispatch sends tokens to the GPU hosting the selected experts, and combine gathers the expert output back. So communication efficiency directly affects the end-to-end inference performance, especially in prefill where many tokens are processed together and communication volume grows quickly. Our target platform is the NVIDIA Hopper GPU. The important hardware component here are the stream multiprocessors, or SMs, the register files, HBM, and especially the Tensor Memory Accelerator, or TMA. TMA is designed for asynchronous memory movement and become critical to our design. If we look at the basic inference schedule, attention is followed by dispatch, then expert MLP computation, and finally combine. This sequential process is simple, but during communication, many SM resources are not used for tensor computation, which already hints at its inefficiency. To improve utilization, previous work introduced two microbatch overlapping, or TBO. The idea is to overlap communication from one microbatch with computation from another. This indeed improved overlap, but it also creates contention between communication kernels and tensor computation. And this is our first key observation. Under TBO, communication still occupies too many SMs. On an NVIDIA H20 with 78 SMs, DeepEP can occupy 24 SMs during the prefill communication. That leaves only 54 SMs for computation and about 69% of the full GPU compute capacity. So the next question is, where exactly are those SMs being spent? We profile the communication path carefully and find that the problem is not just the communication itself, but also the data movement surrounding communication. The important takeaway is that the communication workflow contains several stages where WOPs are used mainly for moving data rather than doing useful tensor computation. More specifically, DeepEP keeps computation buffers and communication buffers separate. Data produced by attention must be copied into an RDMA send buffer, and later copied again through an NVLink buffer into the final tensor buffer. These redundant copies consume a large fraction of communication WOPs. Our second observation concerns bandwidth. Even though NVLink provides very high theoretical bandwidth, the measured algorithm bandwidth in DeepEP is still far below the actual upper bound, both as the EP equals to 16 and EP equals to 32. This means the system is not fundamentally limited by the physical link itself, but by the way the data path is implemented. So why does this happen? The reason is that intra-server forwarding is implemented with the load and store mechanism. Data is loaded from HBM into registers and then stored across NVLink into remote GPU memory. This path relies heavily on the SM execution resources. Unfortunately, register files are limited, while forwarding requires massive parallel load and store operations. That leads to register pressure and even register spilling, so bandwidth remains underutilized and communication becomes slower than it should be. These observations lead to our first design insights. If we can fuse communication buffers with the tensor compute buffers, we can eliminate redundant copies and release SM resources back to computation. Our second design insight is to offload NVLink transfer from general SM thread to dedicated hardware. Hopper provides TMA, which is much better suited for asynchronous data movement than software-managed forwarding based on the load and store operations. Putting this all together, the paper proposes SwiftEP. SwiftEP combines buffer fusion with TMA offloading. Our goal is not just a faster kernel, but a communication design that fits real model serving stacks. The first component is RDMA buffer fusion. On the sender side, SwiftEP fuses the RDMA send buffer with the tensor compute buffer. This means attention outputs can be written directly into the buffer that is ready for RDMA transmission, so an entire copy step just disappears. However, fusion is not free. It creates our first challenge. MoE communication data is small and scattered. In traditional designs, these small pieces can be packed into a continuous communication buffer. After fusion, that packing opportunity is reduced. The challenge is especially serious because the hidden states, routing weights, and expert indexes are all laid out differently. If we send each fragment separately, control overhead rises quickly and transmission efficiency drops, just like this animation shows. So the question becomes not whether fusion is beneficial, but how to make fusion efficient when data layout is fragmented and communication messages are irregular. This issue also interacts with the network interface. Without careful design, the RNIC ends up processing too many tiny requests, and the benefits of moving copies may be offset by extra transmission overhead. In addition, the fused buffer becomes larger, which increases RNIC address translation overhead. The memory translation table cache is limited, so large fused regions can trigger more expensive multi-level address translation. To address this, SwiftEP introduced WQE post coalescing. Instead of posting one word queue element for each tiny segment, we pack multiple scattered segments into one WQE using multiple scatter-gather elements. This reduces posting overhead without reintroducing explicit data gathering. It is a simple idea, but it is important because it preserves the zero-copy benefits of fusion. The second optimization is QP transmission parallelization. Existing systems often use multiple communication channels, but bind them all to a single queue pair. That forces serialized processing inside the RNIC. SwiftEP instead binds each channel to a dedicated QP. Then multiple DMA transmissions can progress in parallel, and the latency of address translation can be hidden across QPs. This is especially helpful once the fused buffer makes the address translation more expensive. The next component is NVLink buffer fusion. Here we fuse the NVLink receive buffer with the tensor compute buffer on the receiver side. The same fused NVLink buffer can also be reused later for combine, so no extra buffer allocation is needed. This reuse is important because dispatch and combine have reverse data flow but compatible layouts. By taking advantage of that property, SwiftEP saves both copy overhead and buffer management overhead. But NVLink fusion creates a second challenge. The sender can no longer rely on temporary receive buffer and later reshuffle data. It must write each token directly to its final location. Yet that final location depends on dynamic token distribution. Our solution is to refactor the notify operation. Instead of sending only the local counts to specific targets, SwiftEP broadcasts the complete token distribution to all GPUs within the server, so every participant understands the final memory layouts. For combine, SwiftEP adopts a pool-based design. This is because the receiver already knows where the data should go, and also SM resources can be saved thanks to TMA in such design. We'll soon get to it when we discuss about TMA. TMA introduced in Hopper architecture asynchronously moves the data between global and shared memory. Moreover, TMAs can reduce register pressure and thread overhead. TMA offloading also faces challenges. How to extend TMA since it wasn't originally designed for remote GPU memory access. By utilizing CUDA context IPC, SwiftEP enables all GPUs within the server to gain mutual memory access to the fused buffers, thereby allowing self-initiated TMA read and write operations to extend across GPU via NVLink. This brings us to TMA offloading for dispatch. We extend TMA to support inter-GPU transfers within a server. In dispatch, the sender loads data and then asynchronously stores it to the receiver. We reduce both thread involvement and register pressures in this way. For combine, the receiver pulls data from the remote GPUs and performs store with accumulate reduction. This lets us offload not only data movements, but also part of the reduction workflow to hardware-friendly operations. And more details are provided in the paper. In implementation, SwiftEP is built on top of DeepEP and focuses on dispatch and combine in inference prefill. The code is about 2,500 lines of CUDA and C++ code. Important engineering support includes multi-SGE transmission, QP parallelization, and a remote GPU TMA abstraction. We test on 2-node and 4-node clusters corresponding to EP16 and EP32. Each node has 8 NVIDIA H20 GPUs with NVLink and NVSwitch inside a server and Rocky V2 across servers. We compare SwiftEP against DeepEP. The evaluation includes both macro benchmark results and an end-to-end serving results on DeepSeek R1 prefill phase. First, SM occupancy. SwiftEP reduces communication SM usage by 50% at EP16 and by 66.7% at EP32. The main contributors are RDMA buffer fusion and NVLink buffer fusion, which remove the data copy WOPs presented in DeepEP. Second, algorithm bandwidth. SwiftEP improved dispatch bandwidth by up to 177.5% and combined bandwidth by 190.7%. More importantly, the measured bandwidth gets much closer to theoretical upper bound, showing that TMA offloading is very effective. Compared to DeepEP, SwiftEP improved the request serving capacity by 21.2%. To conclude, SwiftEP combines buffer fusion and TMA offloading to enable true zero-copy communication and much better NVLink utilization for MoE Inference prefill. The result is higher bandwidth, lower SM occupancy, and better ITPS on DeepSeek R1 prefill stage. And more broadly, we hope this work provides practical directions for more responsive large-scale MoE serving. And also show that communication design should be co-optimized with GPU architectural features. That is the end of this presentation. Thank you. And I will be happy to answer questions to the best of my knowledge as a substitute presenter. Thank you.